Hi, my name is Brandon Bushing.
And my name is Peter Pernada. We are grad students at UB for under the Department for Industrial and Systems Engineering.
Today we will be presenting our final project for IE 555, Programming for Analytics. The goal of our project is to optimize the ride sequence for guests within an amusement park. While we had initially chosen to implement a traveling salesman problem for ride sequencing in Disney World, it soon became apparent that this data was proprietary and not publicly accessible. We then shifted our focus to implementing the traveling salesman problem in Hershey Park in Pennsylvania. The goal of this project is to minimize the total distance for guests who wish to visit each ride within the park. It is based on the nearest neighbor heuristic, which appends the ride that is located the shortest distance from the guest's current location, which is the ride closest to them. This heuristic also incorporates a subtour elimination constraint, so that each ride is only visited once. After generating the optimal sequence, the code will plot the ride locations corresponding to the optimal sequence in a map that also includes current ride wait times.
Let's get started by just running the code. So here we are, it's running. So now we have to input the starting location. So let's just say we are at Skyrush, which is one of the attraction, and we'll use meters. So now the code is running and we just have to wait because it's just looping through all the possible values and just solving the TSP problem that we have. Okay, now when the code is finished running, it'll just create new windows in our browser, as you can see, and it just shows the Hershey Park map. It's pretty neat. You can zoom in, you can zoom out, it's pretty customizable, and all the red dots represents all the rides that exist in the array for the heuristic, which is using the nearest neighbor. So right, so here you go, Skyrush. We initiated with Skyrush, so that's the home location, and the second one should be here, which is Comet. It's based on the nearest neighbor in terms of Euclidean distance, and so on. So the last one is probably, yep, it's this one, Lightning Racer. But that's about it. It shows the order number, the attraction, and the waiting time. And something to know is that the waiting time is all 0. It's because currently the park is closed. Of course, if it's open, then it might have a different value if it's crowded. But this is about it. And if we go back to our code, we can actually see the value of the suggested route. So Skyrush, Comet, Carousel, until Lightning Racer, and also the total distance of. Looking at our code, we just have to initialize it by importing 5 packages, which is pandas and numpys. Those are pre-built, so it's okay, and OpenCage, Plotly, and Amusement, which we have to install simply just going to the CMD and typing pip install the name of the package. So Plotly, OpenCage, and Amusement, and you should have it. It's pretty straightforward. Now we need to get the access keys, the API keys. You can there's 3 API keys that we need, OpenCage, Plotly, and Mapbox. OpenCage, we can just go to the website, create an account, and you'll have it. It's very easy. And then we have Plotly, which again, same process. Go to the website, register, go to account settings, and you should have your API keys here. Just type your password here and you should be able to generate it. And last but not least is Mapbox. You also just have to go to Plotly, go to Mapbox Access Tokens, create an account, and after you have done so, just go to your account and scroll down, and you should be able to find your default public token. Copy that and make sure to copy paste it here, add token, and then also paste it here. And there you have it. Just want to give a heads up, so this HPL is actually the raw data that is printed when you take the data from Hershey Park. So for example here, HPL, it's essentially a listed dictionary. So you see a list of dictionaries within a list that shows all the park names, all the ride names and the waiting times and its associated status. This is a bit messy, so we'll transform them into a data frame later on in order for us to manipulate the data. And as you can see, we have the 2 prompts that we had initially. And this is just a multiplication factor for our conversion from miles, since everything is done in miles for our distances. So in case the user wants meters or feet, we just have this as an option. As I've mentioned before, we want to create a data frame. So in order to extract this list, extract this dictionary, we create an empty list and append the values using a for loop to each of these lists, and then append them using a to a data frame while filtering out all the rows, or the rides that contains no data at all for the latitude and longitude, because bear in mind that our coordinates data are based on Google Maps. So if a ride does not exist in Google Maps, so then there will be no results over here. It'll print out nothing. So that's why we append a value of 0 if an index error, and then we remove all the rows that contains a value of 0, meaning that there is no data. From there, we are able to calculate the distances, the spherical distances. This was actually a function that was taken from Stack Overflow. This is the link to that. But essentially what this does is it calculates the distance between two coordinates in miles, and we actually utilize this in order for us to create the array of distances from the home location to the other to all the other rides, so sort of broadcast the distances. Again, empty list in order for us to append the values of the optimal route consecutively, and we just started out with an initial value of the route distance of 0. Going on, this while loop is actually the block of code that we use to do our traveling salesman problem, that we use to do our nearest neighbor heuristics. Essentially what it does is it appends the attraction name that has the smallest distance from the home location to the route list, and then after that it'll remove that row and then assigns the next nearest location as the home row, so that it'll just keep on repeating the same step until we reach only one row left, where we will then append that value of append that ride into the list. And so now we have an optimized, or like a suggested route for the customers to take. Moving on is the graphing part. So because as you can see in the graph itself, we had some text. For example, over here we have the order, we have the attraction, and we have the waiting time, and that is actually created by this data frame, which we created also just by appending some data for the latitudes and also the waiting times. It's pretty straightforward, I think, and this block of code is actually used to create the content of the map. So like these dots, the latitudes and longitudes are indicated here, and then these here are just some customization items. And also again the text, I created a data frame for that so that it allows us to print out those texts for each of the locations. Last but not least is the layout, which creates the map of this. The only thing that we have to note is this latitude and longitude. These are actually the latitude and longitude of the center of the map where I want them to initiate it. So for example, I want it to be in Hershey Park, so I just googled the coordinates of Hershey Park and this is what I got. So when I set that to these values, when this map first initiates, it'll just pop up with that center value in the middle, and then the scaling will just be based on the zoom value. So if I were to increase the value of zoom to like say 16, then it'll just make this initial scale to a bit more zoomed in, and if I were to reduce that to like say 11, then the initial map will just be a bit more scaled out, like something like this. But yeah, that's pretty much it. Aside from that, it's just the print statements, and that's pretty much it.
From this project, amusement park guests will be more informed of the optimal sequence of rides to visit while enjoying a day at Hershey Park. Given the expensive price of amusement park tickets, it is imperative that guests allocate their time wisely, and the most logical way to do this is to minimize time traveling to the various rides. In the future, this project can be applied to other amusement parks as well. The geocoordinates of rides were sourced from Google Maps through the OpenCage API, and the ride wait times were sourced from Hershey Park through the Amusement API. As long as the ride wait times are publicly accessible for other amusement parks, the code can be applied in a similar manner to these other parks. Finally, amusement park operators can utilize this code for various service-related tasks. Examples include minimizing travel distance for cleaning services, security patrols, or maintenance. We hope that this project is sufficient for meeting the needs of amusement park guests or other related applications.